Now, our choice of non-affirmative priors might not be the most appropriate one in this case. Let's say we are doing this analysis in July, and we know that it is very, very unlikely to be cold outside. We can adjust our priors to be slightly more informative. We can say that the prior probability of it being hot outside is 90%, the probability of it being warm outside is 9%, and the probability of it being cold outside is only 1%. Please pause the video now and try calculating the posterior distribution for the parameter values using these new priors and our old likelihood function. Here are the results of these calculations. To obtain this table, I multiplied the prior probability of it being cold by the likelihood associated with it being cold, and put that number down in the third row of this table. I multiplied the prior probability associated with it being warm outside by the likelihood associated with it being warm outside, and wrote down that number in this third cell in the third row. I repeated the same operation with the values in the last column of this table. Once I obtained these products, I normalized them to add up to 1, and that gave me the posterior probabilities that you can see in the bottom row of this table. Let's try plotting this information. So here on the left hand side you can see the prior probabilities and the posterior probabilities that we obtained in the first analysis. On the right hand side you can see the priors and the posteriors that we have obtained just now. So in the first case, here you can see that the posterior reflects the relative values of the likelihoods. We can see that in our posterior beliefs, the probability of it being cold is significantly larger than the probability of it being warm, which is also larger than the probability of it being hot. When we use an informative prior, then the posterior distribution is in some way a compromise between that informative prior and the likelihood. In these new results, the most likely category, the most likely value of the weather parameter is warm. The second most likely value of the weather parameter is hot, and the third most likely value of this parameter is cold. Now, let's take this example even further. Let's change the data that we have at hand. Instead of observing 4 persons wearing coats and 1 person wearing sandals, let's say we observed 2 persons wearing coats and 5 persons wearing sandals. Please pause the video now and try calculating the posterior probabilities for different weather types using these data and the non-affirmative priors. As before, the first step is to extract the variable values from the description of what we have observed through the window. The value of y, the number of people wearing coats, is 2, and the total number of people observed is 7. Once I apply the probability mass function for the binomial distribution with the parameters specified in our likelihood function and the data, I'm obtaining the following values for the likelihood of being cold, being warm, and being hot. Here are the results of computing the posterior in this case. If you plot the results of this analysis side by side for 2 different data sets, we can see that the direction, the information contained in the data does in fact change the posterior beliefs about the weather, and that shouldn't be of much surprise. we had roughly the same number of observations in dataset 1 and in dataset 2. We observed 5 people in the first case and 7 people in the second case. Let's try looking at the situation when our datasets have the same shares of the people wearing coats and sandals, but differ in the amount of observations they have. We should expect that when we have more observations, the evidence that we have in this dataset should have a stronger effect on our posterior than in the case when our dataset is smaller and contains less evidence for making the conclusions. And this is exactly what's happening here. So here on the chart, you can see 4 analyses. The top row shows the analysis that we performed with non-informative priors, and the bottom row shows the analysis that we performed with informative priors, the ones that we described earlier. The left panels contain the analysis that we performed with the data, according to which we had 4 people wearing coats and 1 person wearing sandals. The analysis shown in the right column are based on the data according to which 40 people were wearing coats and 10 people were wearing sandals. So the data used to perform analysis in the shown in the right column provides a much stronger, much larger amount of evidence for making conclusions about the weather outside. And as you can see here, in both cases, it did update our beliefs about the weather much stronger than the data with fewer observations. And in both cases, we see roughly the same posterior distribution, which should tell you that often when the evidence is strong, the initial prior is significantly less likely to affect your conclusions than when you have a much lower amount of evidence.